Hello everyone, welcome to another video on Calculus 1, and I'm still focusing on the precise definition of a limit. Today I'm focusing on the cubic function. My cubic function is x cubed plus 3. I'm required to prove that the limit as x approaches minus 1 of x cubed plus 3 is equal to 2 by using the precise definition of a limit. So I have looked at linear functions in the previous videos. I've also looked at quadratic functions, and today I want to focus on the cubic function. I'm just going to give you one example. There are two more examples coming up on cubic functions, and then I'll move to rational and radical functions. Just to make sure that if you're watching videos on my channel, the concept of precise definition of a limit should be well understood and mastered. Now, how do we go about this? The solution is set out as follows. And obviously, we have to talk about proof because the question says proof. We copy the question, limit as x approaches minus 1 of x cubed plus 3 is equal to 2. We state the precise definition of a limit. It says if the limit as x approaches a of f of x is equal to L. If this is true, it means for every epsilon greater than 0, there exists a delta greater than 0, such that if the absolute value of x minus a is less than delta but greater than 0, this one here, x minus a is less than delta but greater than 0, then the absolute value of the function f of x minus the limit should be less than epsilon. This is the precise definition of a limit. Now let us translate the given question into the precise definition of a limit. In other words, state the precise definition of a limit incorporating this limit given here. How do we do that? Therefore, we are starting from here. The limit as x approaches minus 1 of what? Of x cubed plus 3 is equal to 2 means for every epsilon greater than 0, there exists a delta greater than 0 such that if the absolute value of x minus 1, remember a is minus 1, absolute value of this is less than delta but greater than 0, then the absolute value of the function x cubed plus 3 minus the limit should be less than epsilon. Now let's simplify this. This implies 0 is less than the absolute value of x plus 1, which is less than delta. Now, after this, we move to our 4 steps. Step number 1, we state what we're given. What are we given? That epsilon is greater than 0. Step number 2, choice of delta. I told you that if the function given is not a linear function, delta is going to be the minimum of the distance should be within 1. So minimum of 1 or the other expression which we're going to determine in terms of epsilon. Step number 3 is the assumption step. So we assume. What do we assume? We assume that this is true. We assume that the absolute value of x plus 1 is less than delta but greater than 0. Step number 4, I call it the notice step. What do we notice? That this expression here always simplifies. X cubed plus 3 minus 2 simplifies to x cubed plus 1. 3 minus 2 is 1. Now I will remind you of factorization of the sum of two cubes. From the lower classes, you must have come across this from the lower classes, that if you have x power 3 plus b power 3 is just x plus b in one bracket, the other bracket should contain x multiplied by itself is x cubed, x multiplied by b is bx. If the sign here is plus, here it must be the opposite of that, and then b multiplied by itself is b squared, like so. So this is x squared there. Please take note of that. X times itself, x squared, and then x times b, xb or bx. There's a plus sign here, you must have a minus sign, and then you multiply b by itself, you get this. Let me give you another example. If you have a cubed plus 8, for example, you can write this as a cubed plus 2 cubed, which translates into a plus 2 in one bracket, and the bigger bracket should contain a times a squared, a times 2, 2a. The sign here is plus, here you must have a minus. That means if I had a minus here, this would be plus. And then 2 times 2, the answer is 4. So using this understanding, you can come here and say, all right, let's work on this one now. Working on this, it means this is exactly equal to x cubed plus 1 cubed, because 1 cubed is 1. And then let's use this understanding to factorize this. You'll agree with me that this is the same as x plus 1 in one bracket. The other bracket will contain x times itself, x squared, x times 1, x. The plus sign here, here minus sign. 1 times 1, the answer is 1. Like so. Which is the same as the absolute value of, excuse me, x plus 1 times the absolute value of x squared minus x plus 1. Like so. And if you check here, we said absolute value of x plus 1 is less than delta. Over here, that means this will be less than delta times absolute value of x squared minus x plus 1. At this stage, most lecturers like using the triangle inequality. I will show you the triangle inequality in my last video on this. I am not a very big fan of the triangle inequality because there's a bit of laziness displayed in it for the lack of a better expression. But at this stage, you take the coefficient of x there, and then you work on this part here. Remember, we said the distance should be within 1. So I'm basically saying the absolute value of x plus 1 should be within 1, like so. Obviously, if you ignore this part here, because we're talking about absolute value, you will put this inequality sign after removing the inequality sign. So at this stage, what does this mean? It means x plus 1 will be less than or equal to 1, but greater than or equal to minus 1. The definition of absolute value, remember that. Now, subtract 1 from minus 1, you get minus 2. Subtract 1 from this middle part here, you get x. Subtract 1 from there, you get 0. Now you come to this coefficient here is minus 1. Divide minus 1 by 2. The answer is minus half. You add minus half there, there, and there. So you have minus 2 plus minus half is the same as minus half. Is less than or equal to x plus minus half is just x minus half. Less than or equal to 0 plus minus half is just minus half. And this part here is minus 5 over 2. Is less than or equal to x minus half. Is less than minus half or equal to minus half. Now I have to square this. Why am I squaring? Because I want to produce the quadratic function that I have within absolute values here. I square this term, that term, and that term. Squaring this is 25 over 4. The inequality sign now must change direction, if you like. And this part here, if you expand, square that part, you're going to get x squared minus x plus a quarter. Greater than or equal to, square half is a quarter. Subtract a quarter from every term here. Subtract a quarter from this, it will be 6. Convince yourself that that is true. Greater than or equal to, subtract a quarter from this, you're going to get x squared minus x. Subtract a quarter from here, you're going to get 0. Right. Now at this stage you can rewrite this to x squared minus x is less than or equal to 6 but greater than or equal to 0. Now you notice that in this expression here we have plus 1, so I have to add 1 here, there, and there. That means 1 is less than or equal to x squared minus x plus 1 is less than or equal to 7. And if I take absolute value of 1, it will be 1. Absolute value of this central part, it will be x squared like this, x plus 1, absolute value of that, less than or equal to absolute value of 7 is 7. This is what I was looking for, because this expression here is that expression. I'm going to take 7 and bring it here. This now will be less than or equal to delta times 7, like so, which is exactly equal to 7 delta. And if you set, let me write it over here, set 7 delta to be equal to epsilon, and solving for delta, this is what you're going to get. Now if you take this expression, bring it in that place there, you're going to get 7 times epsilon over 7, and this cancel, and your answer is epsilon. This should be the end of the proof. But remember what I told you, we want the distance to be within 1 here, the distance to be within 1, and because of that we have to take epsilon over 7, bring it here, and say we want the minimum of the two. Epsilon over 7, we want the minimum of 1 and epsilon over 7, whichever is smaller is what we want to take, and that will complete our proof for today. I will bring, like I said, I'll come up with another example on another set of examples on the cubic function, a little bit more challenging than the quadratic and the linear, and then the radical and the rational, those two are more challenging than linear, quadratic, and cubic. All right, I'll see you next time.